Hello and welcome. Today, we're going to go on an incredible adventure. We're going to follow a single ray of light as it bounces, bends, and ultimately reveals the secrets of the universe itself. I mean, have you ever really thought about it? How do we see the world? More than that, how can a telescope bring a distant star right to your eye, or a microscope show you the hidden world inside a single drop of water? Well, the answer to all of that lies in understanding the path that light takes. In the field of science that helps us map out this journey, that's ray optics. It's our playbook for understanding how light gets from point A to point B, and it's all built on a really simple, elegant idea. Now here's the secret. Light is actually a super complex wave, but ray optics lets us simplify things a lot. We get to treat light as a bunch of perfectly straight lines, or rays. And this model works beautifully, as long as the things the light is hitting, like mirrors and lenses, are way, way bigger than the light's own wavelength. All right, so picture our light ray shooting through space in a straight line. What's the first thing it might do? Well, it could hit something and just bounce off. And that brings us to the world of mirrors and reflection. You know, every single thing you see that isn't glowing on its own, like a table or a book, you're seeing it because of reflected light. But when that surface is super smooth, like a mirror, that bounce becomes incredibly predictable. And that predictability is governed by two really simple laws. So here's the key takeaway. Light plays by the rules. The angle it comes in at, we call that the angle of incidence, is the exact same angle it leaves at. It's like a perfect bank shot in a game of pool every single time. This one simple rule is the foundation for how every mirror, from your bathroom to a giant telescope, actually works. Now, when these rays bounce, they form images. But, and this is a big deal, not all images are the same. A real image is one you can project onto a screen, like at the movies. That's where light rays are actually meeting up. But a virtual image, like your reflection in the mirror, is different. The light rays only look like they're coming from behind the mirror. Your brain is just tracing them back to create the image you see. So how do we figure out where an image is going to show up? We use the mirror formula. Think of it as the ultimate cheat sheet. It connects the object's distance, which we call u, the image's distance, v, and the mirror's focal length, f. With this, we can calculate exactly where that image will appear. It's the physics that makes everything from your car's side view mirror to the Hubble telescope possible. But our light ray doesn't always bounce. What happens when it passes right through something, like from the air into water? Well, it doesn't just keep going straight. It bends, it changes direction. And the reason why is pretty straightforward. Light changes speed when it moves from one material to another. It's fastest in a vacuum, a little slower in air, and even slower in something like water or glass. And this change in speed forces the ray to turn. It's kind of like if you were driving a car from smooth pavement onto some thick mud at an angle. One wheel hits the mud first and slows down, and that yanks the whole car into a turn. Same idea. This bending is fascinating stuff, but it leads to a really wild question. If light bends when it goes into a material, what happens when it tries to get out? Could you, in theory, bend it so much that it just can't escape? And the answer is a huge yes. Absolutely. It's an incredible phenomenon called total internal reflection. When the conditions are just right, the border between two materials suddenly acts like a perfect mirror, trapping the light ray and reflecting it right back inside. So what are those perfect conditions? Well, there are two simple rules. First, the light has to be trying to go from a denser material, like glass, into a rarer one, like air. And second, it has to hit that boundary at a really shallow angle. If that angle is steeper than a certain point, what scientists call the critical angle, it can't get out. It's trapped. Now, why is this so important? Because this one principle is literally the backbone of our entire digital world. In an optical fiber, we shoot tiny pulses of light down a glass thread. By making sure that light always hits the inside wall past the critical angle, it just keeps reflecting millions and millions of times, bouncing its way for miles with almost zero loss of signal. This is how the internet gets to you. Okay, so a ray can bounce and a ray can bend. Now let's see what happens when we get really clever and start precisely shaping the material that it's bending through. This is where we unlock the incredible power of lenses. And really, it all boils down to two main types. You've got your convex lens, which is thicker in the middle. It takes parallel light rays and bends them inward, bringing them together at a single point. And then you have the concave lens, which is thinner in the middle. It does the exact opposite. It spreads the light rays out, making them diverge. That's it. And just like we had a rule book for mirrors, there's a recipe for lenses. The lens maker's formula looks a little intense, but it just connects the curve of a lens's sides, that's R1 and R2, with the kind of material it's made of, N, to figure out its focusing power, F. This is the exact math an optician uses to make your eyeglasses, or an engineer uses to design a high-end camera lens. Okay, we've watched our light ray bounce off mirrors and bend through lenses. So for the last leg of its journey, let's put it all together. What happens when we combine all these tools to see the world in ways we never could before? Well, take the microscope. It's basically a masterclass in refraction. It uses one really powerful lens to create a magnified real image of something tiny. And then you look through a second lens, the eyepiece, which magnifies that already magnified image even more. It's a brilliant two-step process to see the invisible. And a refracting telescope? It uses the same principles, just for things that are unbelievably far away. It has a huge main lens to gather as much faint light as it can from a distant star. And then an eyepiece magnifies that little point of light, making the star seem way brighter and closer than it really is. But there's another way to build a telescope. And it's the design you'll find in pretty much every major professional observatory today. Instead of using a big heavy lens to gather light, it uses a giant curved mirror. This is the reflecting telescope. So why the big switch to mirrors? Well, for a few really important reasons. Lenses can sometimes act like prisms, splitting starlight into a rainbow and making images fuzzy with color. It's called chromatic aberration. Mirrors don't do that. It's also way, way easier to build and support a truly massive mirror than it is to build an equally massive lens. For seeing to the very edge of the universe, mirrors are just better for the job. And that brings our Light Ray's amazing journey to a close. From a simple bounce to the complex instruments that show us distant galaxies, it all comes down to a few simple rules. Which leaves you with one final thought. If learning to control the path of light has shown us this much, what else is out there just waiting for us to figure out how to see it?